8. So, we're gonna talk about optimization problem. So, steps in solving optimization problem. Draw a picture if possible. Label the various parts. 2. Identify the objective of the function to maximize or minimize. Identify the constraint function, solve the derivative and equate to 0, and the roots of the resulting equations are the critical numbers which will give the desired maximum or minimum value of a function. So first example. Determine the area of the largest rectangle that can be inscribed in a circle of radius 4. It says there that the rectangle is inscribed inside the circle. So this will be the circle and this will be the rectangle. Solution. Our constraint function is equals to x squared plus y squared is equals to r squared. This will be the equation of the circle. And the final is x squared plus y squared equals to 4 squared because we're gonna substitute the radius 4. Objective function is area equals 2x plus 2y equals 4xy because the right upper corner of the rectangle will have the coordinates xy. This means that the width of the rectangle will be 2x and the height of the rectangle will be 2y as shown here. Solve for y in terms of x. X squared plus y squared is equals to 4 squared. This will be the constraint function. And y squared is equal to 16 minus x squared because we're gonna solve for y. So the final will be y is equals to square root of 16 minus x squared. 2. Substitute y to objective function. So our objective function is a is equals to 4xy. A is equals to 4x times the y, which is square root of 16 minus x squared. Number 3 is to find the derivative of the area. The area is 4x times square root of 16 minus x squared. The derivative, we're going to use the product rule. So the derivative will be 64 minus 8x squared over square root of 16 minus x squared. We're going to equate this with 0. So 64 minus 8x squared is equals to 0 and 16 minus x squared is equals to 0. This 64 minus 8x squared is equals to 2 square root of 2 and the 16 minus x squared will be equals to 4. So to know the exact critical number we're gonna solve it using the area, the objective function. So 4 times 4 is equals to square root of 16 minus 4 squared, which is equals to 0. And the second is 4 times 2 square root of 2 times square root of 16 minus 2 square root of 2 to the power of 2 is equals to 32. So we're gonna use the 2 square root of 2 for the x. So solve for y when x is equals to 2 square root of 2. We're gonna substitute it with the y equation in the first. So y is equals to square root of 8 and the y is equals to 2 square root of 2. And it looks like that the maximum area will be found if the inscribed rectangle is in fact a square. So for conclusion, since x is equals to 2 square root of 2 and y is equals to 2 square root of 2, therefore the maximum area is equals to 32.
Hi, I'm Catherine Grace Ibacalso from Group 8 and I'll be showing you on how to solve an optimization problem.
So first, we have the steps in solving a optimization problem. First is we have to draw a picture if possible, label the parts. Second, identify the objective of the function to maximize or minimize. Third is to identify the constraint function. Fourth, solve the derivative and equate to 0. And lastly is the roots of the resulting equation are the critical numbers, which will give the desired maximum or minimum value of the function. The question is, a 2 feet piece of wire is cut into 2 pieces and one piece is bent into a square and the other is bent into an equilateral triangle. Where, if anywhere, should the wire be cut so that the total area enclosed by both is minimum and maximum? Before starting the solution, recall that an equilateral triangle is a triangle with 3 equal sides, and each of the interior angles are pi over 3 or 60 degrees. Also, note that if anywhere portion of the problem statement, what this is saying is that it is possible to take a full piece of wire and put all of it into either a square or a triangle. Do not forget about this as it will be important later on the problem. Now, this is another problem where the constraint isn't really going to be given by an equation. It is simply that there is 2 feet of wire to work with, and this will be taken into account in our work rather. So, let's cut the wire into 2 pieces. The first piece will have the length of x, which will bend into a square, and each side will have the length of x over 4. The second piece will have the length of 2 minus x, and we just use the constraint here. And then we'll bend this into an equilateral triangle on each side, and this will have the length, rather, of 1/3 times 2 minus x. The illustration will be shown from this PowerPoint. As noted in the sketch above or illustration above, we also will need the height of the triangle. This is easy to get if you realize that the dashed line divides the equilateral triangle into 2 other triangles. Let's look at the right one. The hypotenuse is 1/3 times 2 minus x, while the lower right angle is pi over 3. Finally, the height is then the opposite side of the lower right angle, so using basic right triangle trig, we arrive at the height of the triangle as follows. Sine pi over 3 is equal to opposite hypotenuse to opposite 1/3 times 2 minus x. Sine pi over 3 is equal to 1/3 times 2 minus x, open and close parentheses of square root 3 over 2 is equal to square root 3 over 6 times 2 minus x. So the total area of both objects is then AX is equal to x over 4 squared plus 1/2 times 1/3 2 minus x multiplied by square root of 3 over 6 times 2 minus x is equal to x squared over 16 plus square root of 3 over 36 multiplied by 2 minus x squared. Here's the first derivative of the area. A derivative x is equal to x over 8 plus square root of 3 over 36 multiplied by 2 multiplied by 2x minus 1 multiplied by negative 1 is equal to x over 8 minus square root of 3 over 9 plus square root of 3 over 18x. Setting this equal to 0 and solving gives the single critical point of x is equal to 8 square root of 3 over 9 plus 4 square root of 3 is equal to 0.8699. Now, let's notice that the problem statement asks for both the minimum and maximum enclosed area, and we got the single critical point. This clearly can be the answer to both, but this is not the problem that it might seem to be. Let's notice that x must be in the range of 0 less than equal to x less than equal to 2. And since the area function is continuous, we use the basic process of finding the absolute extrema of a function. For a0, we have 0.1925. For a0.8699, we have 0.1087. And lastly, for a2, we have 0.25. So, it looks like the minimum area will arise if we take x is equal to 0.8699, while the maximum area will arise if we take the whole piece of wire and bend it into a square.
And once again, I'm Catherine Grace A. Bacalso from Group 8, and that is how you solve an optimization problem.